Today we're going to be talking about something called the Triboelectric Series. I know it looks like a big scary word, but it's really not. It's actually a tool we can use to try to figure out who becomes positively and negatively charged. So let's go ahead and take a look at it. We already talked yesterday about charging by friction, and we know that when we charge by friction, two items have to not only touch each other, they have to rub against each other, and one of them is going to lose its electrons and become positive, and one of them is going to gain electrons and become negative. The question is, how do we know which items become positive and which become negative? We don't really have a way of knowing, and the Triboelectric Series is going to give us that way of knowing. So we're going to be using the Triboelectric Series to determine when you charge by friction who becomes positive and who becomes negative. So the Triboelectric Series, it's just a list of materials, and the ones that are near the top are more likely to lose their electrons, and the ones that are near the bottom are more likely to gain the electrons, and the ones in the middle aren't likely to do either. They're basically neutral items. They don't really become electrostatically charged. And this is what the Triboelectric Series looks like. So you can see it starts with human hands, but really any skin, any of your skin will do, but most of the time it's our hands that rub against something. And then asbestos, which is really bad, and we don't use that very much because that causes cancer. It's used in some like fireproofing things. Rabbit fur, or really any kind of fur. Acetate, which is kind of like tape. Some tape is made of acetate film, tape film. Glass, mica, human hair, nylon, wool, fur, lead, silk, aluminum, paper, cotton, steel, wood, amber, and then sort of more rubbery things, rayon, which some clothes are made out of, celluloids, film, styrene is what they make styrofoam out of, saran wrap is like plastic wrap that you use to cover your food, polyethylene and vinyl are kinds of plastics, and then we've got Teflon, which is sort of what's in your non-stick cookware. So if you have cookware at home that things don't stick to it, it's usually got a surface of Teflon on it. It's a coating. And then silicone rubber, which is different than hard rubber up here. So you notice up here is positive. In the middle here is neutral. Cotton really doesn't react with anything. Steel doesn't really react with anything. Wood doesn't really react with anything. And then you've got your more negative things. So the ones near the top are more likely to lose their electrons, which means they're going to become positively charged. And the ones at the bottom are going to acquire electrons, get electrons, and they're going to become negatively charged. And the things in the middle aren't really going to react with anything. So if you rub cotton on anything, you're really not going to build up any static electricity. So let's look at how we actually use this thing. So how do we use it? Well, if we're talking about two items rubbing together, the first thing we have to do is find those two items. So in the problem, it'll have to say, okay, you're wearing a rayon sweater and it rubs against your hair when you take the sweater off. So you would look up rayon and you would look up hair. So that's the first thing you do. You find the two items on here. The one that is higher will become positive. It will give its electrons up, and the one that is lower down will become negative and will accept those electrons. The farther apart the items are, so if you have something way up here and something way down there, they're going to build up a pretty big static charge, the stronger the charging. The closer that they are to each other, the charge is a lot weaker. So if you were to, rub, let's see, fur with like hard rubber, they're fairly close together. You won't get a super strong charge. They will still exchange electrons though. So when, even if you were to rub two of these these things that want to be negative together, they'll still exchange charges. So the polyurethane will give up its electrons to the polyethylene, but the charge will be really, really weak. You won't see a really strong charge. So you basically want them, if you want to see a big spark, you want them to be separated quite a lot. And if you don't want to have a spark, then you don't want to have items that are really far apart on this chart. So let's look at an example. We're using a hard rubber comb and we're combing our hair. So the first thing we have to do is we have to locate hair and comb. So human hair is over there next to the red arrow, and hard rubber is down, okay? Not quite zero. It's not cotton or steel or paper. And so now all we have to do is decide which thing is higher up and which thing is lower down. So the human hair is higher. It's going to give its electrons up, and your hair is going to become positively charged. And the rubber is lower down, so it is going to take those electrons and it's going to become negatively charged. And if your hair is positively charged and the rubber is negatively charged, what should happen when they are near each other? Should they attract or repel? They should attract. So you might get some flyaway hair where your hair is kind of electrostatically sticking to the rubber comb, particularly if it's a really dry day. All right, so my last point is, why the heck do we care about this? Who cares that we build up static electricity? Yeah, it's kind of annoying when, you wear your socks on a winter's day and your feet rub on the carpet and then you get a little shock when you touch the metal doorknob, but big deal. Or we might have all seen sort of the party trick where you rub a balloon on your head and you make it stick to the wall. Great, that's kind of fun when you're 5, 6, 7 years old, but who cares now, right? Well, it turns out that static electricity can actually be really dangerous in certain situations. One of the ways it can be dangerous is in airplanes. So when airplanes fly, they're flying really fast through the atmosphere, which is air. So there's a lot of air friction. And it turns out that the airplanes can build up static electricity charges on them. So airplanes are equipped with static dischargers on the wings, and I'll show you guys a picture of that in a minute. But basically what's supposed to happen is when the static electricity builds up on the airplane, the little static dischargers are kind of like you reaching for a metal doorknob, and it's discharging the static electricity into the air. Another way it's dangerous is actually at the gas pump. I don't know if you've ever taken the time to read the warnings on the gas pump, but they warn you against a couple of things. They warn you against getting in and out of your car a lot when you're pumping gas. They also warn against using an electronic device like your cell phone. What turns out to happen is when you get in and out of your car a lot, you can get a static buildup. So if you have, let's say, cloth seats, and you're wearing some kind of artificial fabric like a rayon or a polyester, you can build up a static electricity charge on you, kind of like your socks and the carpet. And what happens when you go to take the handle out of your gas pump, you can actually cause a spark, which will cause the fumes around your around the gas pump, because there's invisible gasoline fumes, to ignite. So it can start a fire. Generally, they recommend that if you have to get in and out of your car while you're pumping gas, that you touch the door frame before you go and take the handle out of your car, the gas handle. What happens when you touch the door frame is, because it's made of metal, any static electricity that you build up will then be discharged to the frame of your car, because metal is a good conductor and nothing will happen to it. So please think about that next time you're pumping gas. Make sure you're not building up a static charge. There have been some cases of fires caused by this, so just be careful. A grain elevator, which we don't see a lot around here, but in the Midwest and mostly the Midwest, where they farm a lot of wheat and things like that, they store all the grain in a grain elevator. And what can happen is the grain puts out a lot of dust. And if you go in and you set off some kind of static discharge, you could ignite that grain dust and cause a fire in the grain elevator. So farmers and stuff have to be really careful about when they go in the grain elevator. Lastly, computer memory chips and other electronic devices. They're really sensitive and they can be damaged if there's any kind of static buildup and any static electricity. So a lot of times they're packed in something called conductive foam, and I'll show you a picture of that in a minute. So we've got our airplane wings. If you guys look really closely, you can see these little metal spikes almost on the wings, and the job of that is when the static electricity builds up on the wings, these little things are like little lightning rods pretty much. They discharge the static electricity so that we don't have any kinds of problems with the plane. There's your grain elevator. So inside here is just filled with wheat or barley or whatever grain that you're harvesting or keeping to feed your animals. And like I said, inside there, if there's any kind of spark or static electricity, all that grain dust that's floating around the air is actually really flammable and can ignite. And then thirdly, there is our computer chip, and this is our conductive foam. So if you do any computer work and get computer parts delivered to you, a lot of times they're delivered in this foam. So this foam is supposed to keep there from being any kind of static electricity that could damage the circuitry in the computer chip. So again, your guys' experience with static electricity is more annoying probably than anything else, getting a shock on a dry winter's day. But there are some really serious consequences to static electricity that you need to be aware of, and as you go out into the world, you need to be aware of. All right.